Hello and welcome back to Introduction to Robotics. This is Lecture 2, Part 3. And in this segment we're going to talk about how we physically connect a DC motor to an Arduino microcontroller and learn about something called an H-bridge that is used to actually control the direction of rotation, as we'll see. So, how do we physically connect DC motors to power sources? Well, you could just attach the two motor leads to a couple of battery terminals, that is the plus and minus side of a battery, assuming you had a battery that matched the voltage requirement of the motor or close. And perhaps you've done this, you have a little DC motor and you put one lead on positive, one lead on negative, and sure enough it spins. But what if you want to control the motor? In other words, putting the wires on the terminal doesn't work terribly well for that, right? Really, you need a switch, right? At least you would be able to turn the motor on and off in a measured way. You wouldn't just be kind of making sure it was in contact. Okay, so we can do this with a solid state switch, as shown on the right, which is an electronic version of the switch as shown on the left, right? So you could manually switch it, and in fact you're doing that in Lab 1 in a sense because you have your contact switch in series. But note that there are a couple of things here. One is that we can use a transistor, and in the configuration shown here we're going to use what's called an NPN transistor, and we are controlling the flow of current in the circuit by the potential applied to the base of the transistor. So depending on whether it's allowed to transmit, we either get rotation in the DC motor or we don't. So an NPN transistor will do it for us in this configuration. Note that you need an external power source, and that's shown here as plus V and ground. So that's a battery or perhaps a power supply. Can you do this with a microcontroller? Well, not directly. And why is that? Well, the answer is you can't source enough current directly out of the Arduino board or any other microprocessor, microcontroller that I know of. Generally, they can source about 40 milliamps of current, and 40 milliamps isn't going to be enough to make the motor turn. The DC motors that we have can handle at least an amp, and our H-bridge drivers that you're going to learn about can handle a couple of amps. So that's a lot of difference from 40 milliamps up to 1 or 2 amps. So what are we going to do? Well, we're going to use something called an H-bridge. The other issues are shown here. One is that you can't reverse direction, right? You can either turn it on or turn it off, but whatever side is positive and whatever side is negative, that's going to determine the rotation of the DC motor, and that's that. The only way you could reverse direction is to reverse the two poles of your power source. Another issue is that you can't deal with what's called kickback voltage. So motors are inductors, that is, they're devices that have lots of windings of current conducting wire, and they build up these fields as we saw in earlier slides. And when you turn them off, that energy that's stored in that field wants to go somewhere. And one of the possibilities is that that voltage will try to make its way back into the microcontroller. And that's not a good thing. That's called kickback. And so we want to prevent that from happening. So those two issues are really important for the kinds of things we want to do in robotics. That is, we want to be able to drive the motor in both directions, and we want to make sure that our microcontroller survives, and so we're going to want to address this issue of kickback voltage. So to deal with the first issue, we're going to use an H-bridge, and we're going to talk about that next. The H-bridge in particular is there to allow us to electronically reverse the direction of rotation of the motor. And the second issue, we're going to use what are called kickback diodes. And the motor driver boards that we've gotten from Sparkfun have these diodes installed on them. So as you'll see, that works. Okay, so let's look at H-bridges. The particular H-bridge that's in your kit, and the one that was on the Sparkfun board, is called an L02-3. It's made by a company called ST Electronics, and it can handle up to a couple of amps. So it's sufficient for the kinds of designs we're doing. If you look at this H-bridge, and note in particular, the reason it's called an H-bridge is this part right here. There's a couple of transistors on this side, and there's a couple of transistors on this side. And normally the motor would be shown right here in the middle. Actually, in our case, the motor comes out, and the motor is external to the H-bridge, so it sits up here. But that's how it gets its name, H. So there's one arm, the other arm, and then the middle bridge across. Okay, so there's one H-bridge. Here's another H-bridge. So this L02-3 can actually drive two separate motors. It has a single source of power shown here, V sub S, and this little capacitor here is to do some filtering on that voltage supply, particularly during starts. So as you can imagine, there's a spike in the voltage when the circuit is completed, and this helps to mitigate that. Okay. There are some other devices on here that, as you can see, I've labeled them AGA1 and AGA2, AGA3, and these are AND gates. They're logic devices, and the way they work is if there's a true here and a true here, then you get a true or an on at the output. Otherwise, you don't. Here is one that actually has an inverter on one of its inputs, and that's represented by this circle here. So those are going to be important in terms of how the circuitry within the H-bridge is completed. So each H-bridge has 4 of those logic gates. Over here are the inputs. There's input 1, input 2, and enable. And on the other side, the similar setup for the second motor. We're going to look strictly at the first one since their operations are equivalent. Okay, so if we have a true or on or high on input 1, then we can also have a true or on the enable, and that will be enough to turn on a motor, as we'll see. Correspondingly, and we'll learn in the next schematic why this is true, but if input 1 is on, then input 2 is off or false. Okay. Now, following the line, the L1 in or N1, this dot indicates that these lines are connected. We come up, and so we get a true on the first input to the AGA1. Correspondingly, if we go back to the enable, there's a dot on this line which says it's connected. It's connected here, and it also goes into the second input of AGA1. And so we get 2 trues on that AND gate. On the second AND gate, we have a true coming in on that lower input, but on the input 1 it comes in as true, but it gets inverted, and so we get a false. And so that will determine the output there. On the other side, if we follow this around, we have input 2, which is false, and it's connected here, and it comes into this input here. So sure enough, AGA3 has a false on one input. It has a true on the other input, and you could see that comes from the enable. Okay, so, but that's a true and a false, so true and false is false. On the last AND gate, we have a true coming in from the enable, and then we have a false, but it's getting inverted, and so we have a true there. So it's the case that this transistor, AT1, gets turned on, AT3 is off, AT4 is on, and AT2 is off. So if we follow the current from the power source, it comes down, and here's that dot showing they're connected. Here's another dot showing these are connected. Current comes around to here, and because this base is on, current flows through and out the emitter on this NPN. And note there's a dot here, and it goes on down, but it's blocked here. So it goes out this way to out 1, which is an external connection to this H-bridge. And correspondingly, if we look, the motor is right here. So the other side of the motor is coming in on output 2, and it gets connection here, and it goes down. And because this base is on, current flows through it, down to this connection, and on down. And I'll talk about this in a minute, but basically to ground. This particular part here called sense A is a resistor there to measure the current flow in the H-bridge, and it's used as a safety measure. If too much current would be drawing, you could turn the system off. Okay, so that's how an H-bridge works. Basically, you being the microcontroller, you provide inputs in the form of TTL logic levels, 0 and 5 volts, at the inputs N1, N2, and enable, and those in turn then set up which transistors are going to be turned on and which transistors are going to be turned off. And that then determines which direction the current flows through the motor, and therefore the direction that the motor rotor rotates. If we reverse these and in fact turned on AT3 and AT2, then what would happen is that the current would go out 2 and come in out 1, and therefore the motor would rotate in the opposite direction. And down here in the corner is just a picture of that LM298. Okay, so let's look at this schematic, or expanded schematic, because that's actually several pieces of this Ardumoto V version 13, which is the motor driver that sits on top of your Arduino Uno. Input comes in. There's a couple of different ways it can come in, but basically you can see it comes in through a line here called VN. VN is one of the inputs to the LM298 H-bridge motor driver. Okay. There's also, this is the Arduino over here with different connections. In particular, we're interested in, say, D3, which is the PWM-A, and the D12, which is the direction of A. So depending on what the value is at D12, that is, if it's high, then rotates, I'll say, clockwise, and if it's low, it rotates counterclockwise. And the PWM is what's going to actually determine the power to the motor. Okay, so that's happening in here, and in particular what you see is that you have the a logic device, so that whatever is coming in on N1, it gets inverted on N2. So that's how I can say that we're guaranteed to have a true and a false on inputs 1 and 2. So here's direction A coming on input 1, and then we have PWM, and it's coming in on the enable. So as you saw on the previous slide, that's how you determine where the inputs are going to be applied. I'll just point out over here that these are the output connections, and we have two of them. One is a screw connection that you could clamp a power lead to, and the other is the black Molex connector that sticks straight up, that you can plug your mating Molex pair of pins. And there are 4 of those, and so one of these represents that connector and the other one represents the clamping connection. But attached to each of these leads are these diodes, and depending on where the power is coming from, if it's coming from the motor and what direction, it can flow from the motor into the power source and energize the power source, as opposed to going back through the motor driver. So these are our kickback diodes that are used to protect the system. Okay, well, I'm going to stop there, and we'll pick it up with a discussion about PWMs on the next slide. Thanks, bye.